to show you some examples of limits in engineering and physics applications. So I am a chemical engineering major. So chemical engineering in the most basic form is taking what chemists or what we see in the natural world by research or what we see in the laboratory, like a new reaction we discovered, and converting that process into a large scale process that we can use to make products in a factory, or that can be commercially available to a lot of people. So a really good example of this is before we had fertilizers or synthesized fertilizers, we actually used to cultivate bird poop on small islands off the coast of South America and also the world. And there is a limited amount of this bird poop that we can use as a fertilizer. So a German scientist, he took up this opportunity to discover and basically invent the Haber-Bosch process, which under high pressure and temperature, we can convert some gases in the air, like nitrogen, into usable fertilizers, which is ammonia. So to start off our examples in engineering applications, I'm going to first just review some of the limits and strategies how we can solve limits. So some advice on solving limits, I'll write over here. One piece of advice I have is maybe we can use some math to facilitate or to simplify some limits we might see. They might be a little bit scary, unusual at first. This is definitely true for everybody because it's a new mathematical concept. But through simple math, maybe factoring or even multiplying by a conjugate for those limits with roots, those could help us find the answer to a question you might see. A second piece of advice is visualization. So if you're a person that can look at a function that you see on paper and in text, and you can picture in your mind what that looks like. Or you can even just do a couple of test points, like plug in x equals 0, x equals 1, x equals -1, and see what that looks like on a piece of paper. That'll give you a good idea of what the graph looks like. And then when we look at these limits that approach maybe 0 or infinity or some other random number, you can help predict what that number is by visualizing it. And then the third piece of advice is something you'll hear for the rest of your time in education, and that is practice. So at first, you're going to see when you're doing limits, you're going to make a lot of mistakes, and maybe you're going to guess sometimes, and everybody does this. But guessing is not the best thing. You need to find an answer that makes sense to you, and if you don't, you need to go ask someone for help. You can't ask them for the answer, but you can ask them how they're thinking about the limit and how they got to that answer. Everybody struggles with limits at first, but I'm sure if you do enough practice, you can be very good at it. Okay, so for the first application I'm going to show you guys today, it's going to be something you might see in chemistry class, or if you already take chemistry, you might have already seen it before. So a lot of times in chemistry, we like to look at the rates of reaction. So we want to know how fast something might happen. So we can use calculus actually to derive the concentration versus time plots we see in nature. So we just do simple calculus that you'll learn later on, maybe in a future chem class, and you'll derive these equations. So the first equation I'm going to show you is this. So this equation says A is a function of T. A is just the concentration of some hypothetical chemical we have. So concentration is the amount of something per unit volume. So usually in chemistry we say moles per liter, also called the molarity. So this A naught, we call it 0 naught, and that just means the initial concentration of the substance A. Then we have an E here, that's Euler's constant. You probably learned about that before. And then raised above the E is negative KT. So K is a rate constant. That is something we experimentally find. and you observe it in the lab. And t is a measured variable. This is something we're keeping track of the time, and then we're measuring the concentration of the substance A. So it's not the measured variable, it is our dependent variable. I mean independent variable, sorry. I always mix them up. So this does not rely on something. The independent variable is something that we use along the x-axis typically, and then the y-axis is something we measure, the dependent variable. Okay, so first of all, so if a of t equals a naught e to the negative kt, I'm going to ask you this question. So what is the limit of t approaching infinity of a of t? So also a lot of times in engineering math, we like to use general variables instead of putting numbers here. So a naught is just a number in reality. So if we use this in real life, a naught is a number. But for now, we're just going to keep it a letter for simplicity, and you can apply this to chemistry in the future. So let's do the first way I suggested doing limits, and that is with math. So if you like doing math, this is a great way to learn how to do limits. So let's do the math way. So this is equal to, I'm just going to write it out, t approaching infinity of a naught e to negative kt. So that's just a regular equation we're doing here. A of t is this, so we're looking at that. And then let's just simplify this a little bit so we can understand this equation a little bit better. So we know that negatives in the exponent area over here, that means that it's actually in the denominator. So we're dividing by e to the kt. So multiplying by a negative kt, e to the kt is the same thing as dividing by e to the kt. So now let's think about this. If t is approaching infinity, and infinity is not a number, it is a concept, we can imagine this t going from 0 all along to the right along the x-axis. So what that means is that t is going on for infinity, to the end of the universe. But we can think about it as going to a million, 10 to the 6th, 10 to the 9th, a billion, a trillion. So what happens if we put a million in t, if we plug in a million into t? Well, that means we put e times k times e to the k times a million. What is that? That's a really large number. So if you remember exponents, they grow exponentially, of course. So if we're at t equals 1 million, that's e raised to the k times 1 million power. That's really big. So what happens if we have some number divided by a really big number? And a naught is on the magnitude of around 1 or 10. So something really small compared to a million, a billion, or a trillion. So when we divide something smaller by something bigger, we usually approach 0. So the limit of t approaching infinity of a naught e to the negative kt is equal to 0. So what's important to understand here is that we never get to infinity, and we're only approaching it. So now let's attack this question from the visual approach. So I drew an XY plot over here, or I'm about to. And on the x-axis, we have our independent variable, t, measured in seconds or minutes, it doesn't really matter. And then a of t, which is our concentration. So our a naught, as you can see here, is our initial concentration because this is t equals 0. So now let's think about this. This is e to the negative kt, so if you remember from algebra, e to the negative x, that is going to be an exponential decay. So we're going to see something like this. So as you see here, we're exponentially decreasing the amount of A in the mixture. And this, or I should have put the dash line here. So as you can see, it is approaching 0. It never gets to 0. And that is because if you learn a little bit about chemistry, the amount of reactants and products really determines how much a reaction is going to proceed and how much A is going to be consumed. And that will never be 0. We can never measure it to be 0. And that we can see that in the limit here. So this is going to go on forever, approaching 0, closer and closer, but you'll never see that. So if you knew how to draw this graph, then this is another great way to interpret a limit. So if you had the question over here, and you graphed it out like this, you did some test points, maybe here, here, and then maybe you plug in 1,000,000, and you get something around over here, t equals 1,000,000. Then you're going to see that it's getting closer and closer to infinity. So both are closer and closer to 0, I should say, as you approach infinity. So as you can see, both ways are really great ways to understand how to do limits in real life applications. So another great way to understand limits in the real world is from physics as well as chemistry. So later on, you might learn about springs in physics and oscillations. So if you remember sine and cosine or trigonometry, those waves are periodic. They have an amplitude, a wavelength, a frequency, and it's motion that happens consistently and repeatedly, you should say. So we can think about a spring in motion. So let's say we have a spring here, and we have a mass. We give that mass little m. So some things about the spring, you don't need to understand this, but I'm just going to show you some applications. So there's some qualities of the spring that we care about. So if you remember from physics, we have Hooke's law, which is F equals so if you remember from physics, sorry about that. If you remember from physics, we have some qualities about the spring. So we have the constant K, which is newtons per meter. So this is a spring constant. We care about this because it shows us, depending how much the spring stretches, it's gonna increase the amount of force. So you can think about this: if you have a spring at equilibrium, that means you're not pushing or pulling it in any direction, and you move one end farther from the other end, you're gonna feel a greater force on your hands. And let's say we move this mass down here, some distance, y, you should say, and as soon as you release the spring, you're going to go see the spring move up and down, up and down, up and down. And if you graph this motion of the seconds versus the height of the mass, you're going to go see periodic motion like that. If there's no friction, if there's no drag force from the air surrounding it, if it's the perfect situation, you're going to have this perfect sine wave. But what about the case where we do have friction? So later on, if you do take engineering courses, or if you're in a STEM field later on, you might have to take linear algebra, and then you're going to understand, or maybe from those physics classes, you're going to learn from linear algebra the solutions to this problem. So if we skip a bunch of that math, and I'm just going to show you the solution. So let's say we have a mass on a spring with some spring constant K in the mass, and it's going to go down some height, doesn't really matter. We're going to see that we can plot the height of the spring versus time, or we can find the equation for the motion with time, and this is the solution if there is friction. So if we have the height as a function of time, we're going to see that we're going to have e to the negative t times cosine of, let's say, 10x. So what happens is that we get this another exponential decay part of this equation, and then we have some trig function over here. So let's try to solve a limit with this function. So what happens to the spring, or the motion of the spring, as t approaches infinity? Sorry about that. As t approaches infinity, what happens? That should be t. So we have a variable, an independent variable here and there. So what's going to happen? Lots of times you might refer to this of who's going to win the race. So if you might recall from class, if you have a limit of a trigonometric function, just like t approaching infinity of cosine t, that means it's going to be going up and down forever and ever, and you'll never approach a finite or a singular point. It's going to keep on going up and down, so we say the limit does not exist. But does this exponential decay affect any of that? We can use something called the squeeze theorem. You may learn this, you may not, but I can show some simple math to understand the squeeze theorem. So I first want to write the cosine of 10t. This is a periodical function. It's moving up and down, and it's always between 1 and -1, if you recall the unit circle. I have nothing in front of cosine, so it's always going to be 1 or -1, or in between. So we can say that cosine of 10t is always going to be less than or equal to 1 and greater than or equal to -1. Okay, simple fact right there. So even with these inequalities, I can multiply every component of the equality and it's going to be correct. So I'm going to multiply it by e to the negative t. And what's going to happen? We're going to get negative e to the negative t is less than or equal to e to the negative t cosine of 10t, which is less than or equal to e to the negative t. So now again, we can think about this in two ways. So we see our function h of t is in between these two functions. This is why we call it the squeeze theorem. So this is where visualizations will help you out. So if we're going from 0 to infinity, let's plot negative e to the negative t. So remember, if we have a negative in front of the function, that's going to mirror it across the x-axis. So if exponential decay looks like this, we're going to get something that looks like this, roughly. And then the upper limit, or the upper part of the function where it's being squeezed, is e to the negative t, which is that exponential decay we saw earlier on. So it's going to look like this. And then now we can say that negative e to the negative et is less than or equal to our function h of t is less than e to the negative t. We can say that h of t is in between these two functions. And another fact we do know is that we have this wave function here, a periodic function that's going to be moving up and down, always in between these 2 points. So that means we're going to have something like this. So as you see, our cosine wave is being squeezed by the upper and lower limits, and it's going to approach a point because of the upper and lower limits. So what are the limits that these two functions are approaching? We already knew from the past question I asked you that the limit of t approaching infinity of e to the negative t is 0. Because remember, 1 over e to the t, if we have a t equals 1 million, that's 1 over a really big number, and that is 0. So as you can see, our function is being squeezed to the point where it reaches or will reach or is approaching 0 at infinity. So a main takeaway from this problem, so in the future you might see the damped motion of an oscillating spring moving up and down. What that means is that we have a spring, we move it down a little bit, and we have a mass. It's going to move up and down, but we have friction acting on it, so it's going to slow it down, or it's going to go less frequently, and that will make our spring stop or approach stopping at a point. So now you know, if you have an oscillating spring, this is some way you can solve it, and you can use limits to understand physics and some chemistry applications. Thank you for tuning in today. Hopefully I'll make another video about derivatives in the future and all the ways we use them in my field and in others too.